map, it's at the base of our application. And right now, given that we have this control over what goes into the map and we are able to build the features that our customers need, we also need to find a way to make the data more local, or to localize the data and be able to introduce this hyperlocal data into the map. Basically, as I mentioned before, we operate in 8 countries, which are very different from one another. So each one of these countries has its own specific. So we'd like to have the chance to introduce this specific also into the map. Quick introduction. I'm Roxana Crișan. I'm head of engineering in geomapping, and I'm also the site lead for Grab Romania R&D Center. So right now, our focus here is to build the best maps for Southeast Asia and beyond. And my plan is to introduce it to an intriguing solution that we found to an expensive big data and computation from our map compilation pipeline. As I mentioned before, we operate in Southeast Asia, so in 8 countries, and our scope is to build the best maps for Southeast Asia, but also beyond Southeast Asia. And we do this by delivering an OSM-enriched map to our consumers. It means that we add data into the map, data that in the end will support the services running on top of the map, like the turn-by-turn navigation or the allocation process into our super app. Okay. So basically, we have this large map, big area of Southeast Asia, and we need to localize each road that's part of this area. It's a challenging problem, and we need to also do this in a very efficient way, because our scope is to deliver the map every day, so with a high frequency. For the sake of this presentation, we are going to use this extract from Southeast Asia. So you can see here an example of the roads in the area. And here it's the same area, but you can see only the borders for that specific area. Basically, what we want to do with the data that we have is to extend all this information that is specific to a certain area for a country, for example, in this case, and apply it to the roads that are part of that area. For example, on a country level or on a border level, we can know the official language of that country. We can know the driving side for that specific country. So basically, we can transform and move all this information at each road level and use it in providing a better experience in our navigation or in our super app. So what we want to achieve is basically take all this information from the colored borders in this image and apply them to the area inside the border, basically to the entire area of the country. And we can do this just by overlapping these 2 areas and transforming and moving all the information from the area itself to each road that belongs to that country. But now the challenging part comes in. We need to be able to localize the roads. We need to be able to know to which country a road belongs to. So again, we aim to be hyperlocal, but at the same time we want to deliver the map daily with a high frequency. So our problem is that the straightforward solution, where we test for the inclusion of each road in each area, in each border that we have, it's a very costly operation. It costs us a lot, both in terms of cloud cost, but also time, because we have a geometrical operation of inclusion, which is quite complex in case of a line and a polygon, but also because we have a large amount of data. We have almost 30 million of roads and more than 10,000 borders for the area that we consider. So our solution for this challenging problem was to switch and replace this expensive computation with a distant approximation. What this means? It means that we are going to introduce a proxy entity. We are going to use an intermediary medium for the localization of the roads. And instead of that big, large operation of localization, we are going to split it into smaller operations that can be run individually. For example, we can have an inexpensive pre-computation and an inexpensive or less expensive use of those pre-computed values. And of course, given the large volume of data, we can leverage the big data techniques to distribute the execution across many nodes. Okay, before going any further, I want to stop for a moment on the concept of geohash, because that's a new concept that we introduced and we are widely using in all our work. Basically, a geohash is just a way for us to represent a certain region on the Earth. We start by just splitting the entire surface of the Earth into 32 regions, and then we go deeper and we split again each region in another 32 sub-regions and so on. And we go as deep as we need, and as we advance, basically the number of the characters that uniquely identify the geohash or that region, specific region on the map, also gives us the precision of the geohash. To give you an example, geohash level 1 size, it's around 5,000 kilometer wide per 5,000 kilometer high, which is one of the original or initial geohashes that we have. For a geohash of 6, we have 1.2 kilometers per 600 meters, while for a geohash of 9, around 5 meters per 5 meters. So you can see that they can be quite accurate depending on the needs of each of these application or use cases where we apply them. For example, here you can see a geohash 6, a precision 6 geohash. Okay, now going back to our problem. We aim to localize all these rows that you can see here in blue on the left side, but it's an expensive operation because we need to test for the inclusion of each of these roads inside the border, right? How expensive? We don't really can say because it depends a lot on the data that we need to work with. It depends on the complexity of the border, it depends on the complexity of the road geometry. But we can try to see if we can find a cheaper or an easier operation to run. So testing for inclusion inside the square should be simpler, should be less expensive than testing for an inclusion in this complex polygon on the left. So basically, what we decided to do was just to take the entire area and split it into regions, into geohashes. Then we take also the roads and we try to identify all the geohashes through which a road goes through. Basically, now we have the geohashes that belong to a certain area or to a certain country, for example, and we have the geohashes through which a road passes. All that it remains to be done is join these two data sets, and as I mentioned before, we are doing in a big data style to distribute as much as possible this operation. But using this approach helps us a lot. It reduces the cost of the operation, but we also trade precision for cost. This means that the cost goes down, the computation time, the amount of hardware that we need, but also the precision goes down, because roads that are very close to the border might be wrongly classified. They can be marked as belonging to a certain country, which might not be true in certain situations. So for example, if we go back to, to this initial situation, we have the road on the left, which is outside of the border. If we apply our geohash approach, you can see here that the roads goes through these 3 geohashes. But when we localize the geohashes, this geohash in the middle, we see that it belongs a bit, but it belongs inside the border that we consider. And because of that, we wrongly localize this road. We say that it belongs to the area, to our area of interest, when obviously it is outside. So what we can do to improve this precision and not lose the gain that we had with the cost? So we can increase the geohash precision. I mentioned before that we are using, or we can use different precisions. We can start with a higher precision, so larger regions, and we can continue to split them into smaller and smaller geohashes. As you can see, as we go deeper and the regions are smaller, they better reflect the border. But again, here, we need to be very careful to not to lose the advantage that we gain by simplifying the border. So we need to find the right balance between precision and the size of the geohash that we are going to use. So that would be one option for us to increase that precision. Another option would be to compute the coverage percentage. This means that we can look for each geohash and decide if it belongs or not to the area that we consider. For example, for this geohash, we can clearly see that it belongs to the border, to the country. So we can say that it has like 100% coverage inside the country. So we can say for sure that it's localized inside that country. If we take this case, this geohash, it's maybe around 80% inside the country. So maybe we can still take the risk and say that this geohash belongs to our area of interest. But if we go to this, again, to this small geohash on the left, we can see that only a small part of it, like 5, maybe 10%, belongs to the area. So for these kind of situations, we could just decide not to consider those geohashes as part of the border or our area of interest. So that's another way that we can increase that precision. And of course, the third option, or the third solution that we have to increase the precision would be to keep part of the border geometry in the geohashes that touch the border. What this means is that if we take this geohash, for example, when we try to localize the roads that are inside that geohash, we'll use the simple rectangular form of the geohash. But if we take a geohash which is closer or intersects a border, we can just cut that geohash using the form of the border. So basically, we end up with a more complex form for localization, but this will impact only the geohashes which are located at the border. So we kind of complicate the operation, but we gain precision here as well. So now going back to how complex, how difficult this operation is, and what's the gain with the approach that we use for this specific problem. I mentioned at the beginning that we have a lot of data that we need to localize. We have around 30 million of roads and more than 10,000 borders. So we took a very small amount of this data, around 180 borders and around 400K of roads, from that area, and we tried to run a comparative analysis between the two approaches. So if we look at the straightforward solution, the brute force solution, you can see that it took us around 38 minutes to localize these roads. But when we applied the geohash solution with our intermediary entity, the time went to 1.3 minutes. So you can see it's a big difference and a big gain in terms of performance and running time. But probably you see that there is a star there. This means that basically here we didn't really compare apples to apples, because when, as I mentioned at the beginning, our geohash approach needs a pre-computation phase. It's the phase in which we need to fill all the borders with geohashes, so that we know for each geohash to which country it belongs to. So this pre-computation, it's still some kind of expensive operation, and its running time depends on the number and the shape of the border geometries, the precision of the geohash that we use for localization, and of course, on the hardware that we have available for this. But one important aspect, this pre-computation, it's run very rarely, because the borders, especially if we work with country borders or administrative borders, don't change that much. Very rarely you need to change a country border, so you need to rerun this localization at country level. So, although it is an expensive operation, it's something that can be run once and reused for a few times. For example, we can run it every month, or we can run it every 6 months, again, depending on the nature of the borders that we consider. In our case here, we work a lot with country borders or with administrative borders, but we have other use cases that can be applied where borders can be used. To give you an example, in Southeast Asia, in some countries, we have some specific areas where our drivers, the access for our drivers, it's difficult. So in order to improve their experience, we are trying to exclude the roads that cross those areas from the routes. So we localize those roads, we identify the roads that belongs to those specific areas, and when we need to calculate a route, we just exclude them from the routes. Now, the regular computation, the one where we find the geohashes for each road, it's something that is run very often, because the roads, especially in OSM, our base map change frequently. Continuously, the community and everybody that is using OSM comes in and adjusts the geometry or adds new roads. So this part needs to be run as often as possible. So at the end, once we have this localization in place, you can see here how we mix all these approaches. Basically, at the border, we cut the geohashes by border, but we also use smaller geohashes to better reflect the form of the geometry. But inside the border, where we have geohashes with 100% coverage inside that area, we can apply the reverse logic. We can merge them back into larger geohashes and again simplify the geometry that we use for the localization of the roads. So that was the way that we apply this road localization. One of the many steps that we have inside our map-making pipeline, but I would say one of the base steps, because on it relies, all the others rely on it. So, thank you.
Thank you, Roxana. If you have any questions, if not, I'll just Okay.
Thank you. You mentioned the pre-computing that we're doing when the borders change. Why are we doing it at a certain frequency, like 6 months or 3 months or something like that? Why don't we just detect where the change is and recompute only what's affected, the smaller geohash that's affected by the change?
That's one way of doing it. Right now, the way that our pipeline is built is just has this batch approach because we leverage a lot the big data part. So it was just a choice that we applied for the way that we approach this operation. For our use cases, it served us well for the until now. But yeah, what you mentioned works as well.
I was thinking to ask you because I think in April we got a nice presentation with Carta camera. So the camera that the drivers are using it. So how that connect with the maps?
Basically, the Carta cams are the source of information that we use to enhance our maps. We use the Carta cams to collect fresh imagery from the ground, and then we process all that imagery and we extract information regarding the map, regarding the roads. For our use case, is the map. It's traffic signs, especially traffic signs, which then after that are introduced into the map layer.
Okay, so basically you update, I don't know, daily or once per week based on the information you got?
Yes, we generate the map daily. We update it based on the requirements of our services. Right now it's weekly. It's just we decided that it's enough weekly, but other than that we generate it daily.
And how big is the database?
For the map?
Yeah.
I don't know. A few.
Okay.
5 gigabytes.
Okay, that's good.
For CartaView, are you asking the imagery or the map itself?
The map itself, I was thinking, but yeah, CartaView is different.
The map it's right.
Okay, yeah, I see. And you are still using OpenStreet?
Yes, OpenStreetMap, it's our base layer for the map. We use the data format, we use the PBFs in which OSM comes, the format that OSM uses.
Nice.
So we are fully OSM compliant at this level, yes.
Perfect. Okay, any other questions? If not, we will move to the panel. Right? Okay, let's give Roxana a round of applause.
Thank you.
Yeah.